All right. So next up, let's move into the keynote talk section. And it's my great pleasure to introduce to you Professor Yejin Choi. So Yejin, please come forward, and we'll have her set up here. Probably the most talked about advancement in technology is the rise of ChatGPT and all these other massive scale neural networks, right? So these large models, every discipline, including our own, has been struggling to figure out what's our answer in response in the face of these Goliaths. Well, Yejin is here to advise us. So she is the Brett Helser Professor of Computer Science at the University of Washington, a distinguished research fellow at the Institute for Ethics in AI at the University of Oxford, and the senior research director at the Allen Institute for AI, and she's leading the Mosaic project that focuses on common sense reasoning. She's won numerous accolades, including 7 base paper awards and 2 test of time awards, and not only that, also the 2022 MacArthur Fellowship, which is widely known as the Genius Grant. So I'm a big fan of her work, especially after hearing her very, very insightful talk on TED. So I just can't wait to hear her live in person. So without further ado, here is Professor Yejin Choi.
Well, thank you so much. It's such a great honor to give a keynote at VLDB. When I was a PhD student, database was one of my favorite classes to take. And I was, to be honest, fairly intimidated by the, how beautiful concept there is that people have already developed. So I decided I'm going to do NLP, which seemed messier. And yeah, I don't know what happened with this MacArthur thing, but I thought that I'm really far from being able to make an impact in this database field back then. But anyhow, yeah, the frequently asked questions these days is this, that whether NLP or common sense and whatever you want to put in the ... has been already almost solved by ChatGPT. I'm going to get back to this toward maybe later part of the talk, about 25% of the talk later. But first, I want to address why we are even having this issue. It's really the scale that unlocked these amazing capabilities of neural networks. And it feels like, especially being in academia, that this is a situation of David and Goliath. So, I often get asked these questions from media that, am I sure that we can't reach AGI just by scaling things up? And also from academia, the concern is, can we do anything impactful without extreme scale compute? So we can seek inspirations from classics such as The Art of War, which in my interpretation says, know your enemy, choose your battles, and innovate your weapons. We do need to reinterpret that in the modern deep learning context. So know your enemy means evaluation with scrutiny and realism, including adversarial and out-of-domain distribution examples. And then choose your battles might be about coming up with new task formulations and leaderboards. And finally, innovate your weapons is where we can innovate algorithms and data that doesn't require as much compute. So my research centers around all 3 themes, but today I'm going to focus primarily on the third portion, which is how we can innovate algorithms and data. So the first part will be about inference time algorithm, and what I mean by that is basically answering the question of how can we fuse logical or symbolic reasoning on top of already trained neural network that is just neural black box. So can we put interpretable symbolic algorithm on top. And then the other part of this talk is going to be about symbolic knowledge distillation, which is about how can we fuse semi-structured knowledge into the training process of neural language models so that neural language models might have a bit better knowledge that it couldn't have during pre-training. And for each of these themes, there are several papers, but I selected just 2 under each bin as a case study to highlight. So let's begin with maieutic prompting under the inference time algorithm umbrella. So it starts with this observation that language models are sometimes amazing. So for the time being, we're using GPT-3. So that's because at the time of this the publication, at the time of the publication, GPT-3 was the best model, but this applies to later GPT as well. So if you travel west far enough, from the west coast, you will reach the east coast, ? Then GPT-3 says, yeah, the world is round, so you can eventually reach, therefore this statement is true. So that's pretty impressive, except when you ask a lot of different questions in different ways, sometimes it's conflicting its own previous answer. So at that point, it's not clear what does it know and not know. And depending on whom you ask, by the way, some people only cherry pick what didn't work, and some people only cherry pick what did work, and then conclude entirely the opposite conclusion. So it's interesting time for sure. So the spirit of this work is how can we make lemonade out of these juicy lemons? And perhaps one approach can be to get philosophical and use the Socrates maieutic method. And by the way, Socrates suggested this because humans are also inconsistent. It's not just the GPT-3 to blame, but it's ourselves to blame as well. So the way it works is something like this. So we start with the same question we saw earlier, just smaller, but it's the same question. And we append the answer true, because, and then let GPT-3 to complete the following sentence. So then it's trying to now rationalize why the answer is true, which is pretty good. But if you ask the same question by replacing true with false, and you're forcing the GPT-3 to rationalize the incorrect answer, now it's just saying a bit of BS explanation. So it kind of knows that there's something odd about that answer. That's good. So by the way, what we have so far here is E of T and E of F. So that means explanation to support the answer being true and false, respectively. So we can do that for its own explanation as well. So we give its own explanation back to GPT-3 as a question and let it decide whether it's true or false. And so in one version of it, we negate what it said, and then see whether it's able to flip the answer. So if it's a logically consistent machine, then it should be able to do that correctly. But of course, GPT-3 being GPT-3, or ChatGPT even does that too, if you keep asking this, then sometimes it's not able to flip the answer, even though it's negated the sentence. So here is where it kind of knows that there was something odd about its previous BS explanation supporting the answer being false. I know it's a lot, by the way, in the morning, so I'm just giving you some broad stroke sense of how, depending on how you do this, you can discover logic inconsistencies in GPT. Now, we can do this recursively, basically building this tree of maieutic reasoning, maieutic prompting. And at this point, we retain only logically consistent portion of the graph. But even so, there will be inconsistencies across different portions of graph. So what we then do is to look at the global consistency across the entire graph by first looking at the node level confidence score, and then we also look at edge-wide consistency using a tool called natural language inference. It's a tool in NLP field that can tell you whether there's a contradiction in a pair of a statement, or whether one is entailed from the other, or whether one contradicts the other. So using that, we can then build a constrained optimization problem. And the funny thing here is that we use this weighted max set solver from 2001. You know, it's almost like people tend to throw away these beautiful algorithms from decades ago as something irrelevant in the face of neural language models. At least, you know, this happens a lot in the NLP field right now. But the truth is, there's something really powerful in these classical algorithms that can fix the problems in the currently powerful neural models as well. So we do that, and the final truth assignment given to all these nodes in the graph can be interpreted as, you know, whether the original, the final answer to the original question should be true or false. So if we do that, so in the evaluation, CSQA is common sense QA benchmark, and if you do at the chance level, then your accuracy will be 50%. It's true, false questions. So the green is the canonical prompting using GPT-3. So GPT-3 used to be quite bad. You may have heard of chain of thought reasoning. How many of you heard of chain of thought reasoning? Just to get a sense of the, okay. So it's some, you know, people using ChatGPT found that if you ask ChatGPT to think step by step, just, you know, say that in natural language, then it's actually able to think step by step and then perform better on its own. So that's basically what it is. And then, so that's yellow bar. And then other people come up with a little bit more better ways of doing it. But basically, our performance is the pink bar, which does more elaborate inference on top. So you see the performance gain is quite drastic. And it's doing even better than supervised method, meaning you download your pre-trained model and then train on some target task in a supervised manner. Usually this one is hard to beat, but in our case it does. And then the pattern, similar pattern was found across different common sense benchmarks that came out in recent years. So the key takeaway message here is that Socrates' myotic method not only enhances flawed human reasoning, but a computational interpretation of it can dramatically enhance flawed GPT-3's reasoning as well. So that's one example of how can we fuse logic or symbolic reasoning on top of already trained and not very logical neural language models. Let me switch the gear a little bit. I know we haven't done the neurologic decoding. We'll get back to it. But let's look at an example of a symbolic knowledge distillation for a change. So here the question is, instead of incorporating algorithm during inference time or test time without training, can we actually train the underlying model better with a somewhat structured notion of knowledge? So in particular, in this work, we focus on building causal common sense models out of general language models. So for the purpose of this talk, the definition of common sense is loose. It's the basic level of practical knowledge and reasoning concerning everyday situations and events that are commonly shared among most people. The definition is loose in the sense that who knows what I mean by commonly and the most? It can be anything. But it is really the gist of our common sense in the sense that, you know, we generally probably agree that it's okay to keep the closet door open, but not as okay to keep the fridge door open. because the food inside might go bad. But all of these rules of thumbs can be violated or irrelevant if there's additional context. For example, what if the refrigerator is not even hooked up in the wall yet? There's no food inside. Or there's a food, but it's just like dried pasta, then it doesn't matter. So there are always additional contexts in which this reasoning can be defeasible. So that is the amazing thing about our common sense that also makes it uniquely challenging for computational algorithms, because things are so loose and messy here. So this is essential for humans to live and interact with each other in a reasonable and safe way, but AI tends to lag in these capabilities. So the underlying idea behind this is that language models are not equivalent to knowledge models. Maybe similarly, language models are not database models either. So under that premise, we worked on building symbolic common sense knowledge graph as well as neural counterpart of it. So neural common sense model is trained on top of symbolic knowledge graph as if that's just another source of text corpus. And up until 2-3 years ago, the symbolic version was fully human-written databases. So we kept working on this, but again, things were fully crowdsourced by humans. Let me show you what sort of a semi-structured knowledge there is. So imagine a situation where you get your car repaired, and immediately a number of inferences may come to your mind. So maybe as a result, you need to call Uber or Lyft for a ride. You may need to pay the bill. Beforehand, you need to find a mechanic, and you probably need money, and so forth. So you can reason about preconditions, post-conditions, post-effects of this event. You can also reason about what sort of object-centric knowledge you can have. So money is typically used for paying bills, but you can also fold that into origami if you so desire. You probably never did that. I never did that either. Someone wrote this for us. But it's possible that we reason about this even if you've never seen anyone doing it before, because you understand the true property of the object. And so we crowdsourced all of this for some time. And to the point that it accumulated until it had a 0.3 million if-then inference rules over 23 different inference types or relation types or edge types. So by the way, I will lift these constraints that we have to do this manually in a bit. But you might wonder what good does it serve. So when we trained neural model on top of this symbolic knowledge graph and compared to GPT-3, which was so large, it couldn't even fit into the slide. It's more than 400 times larger than the COMET, which is tiny little neural language model. And then compare the performance of the common sense predictive power. So basically what we do is we give one node and then one edge type, and then let it generate whatever else it follows. In the previous graph you saw, there's just one node given, one edge type given, and then let it generate, and human decide whether this looks good or not. So you see, GPT-2 used to be very bad. It was, 36% good. GPT-3, just by scaling things up, is remarkably better. 73% good, that's really quite something. But, it's too large. It doesn't fit into anybody's laptop. So COMET, much smaller, but does do much better. So that's nice. So since we released COMET/Atomic, which are neural and symbolic common sense resources, a lot of people all around the globe did lots of creative things. Sorry, I clicked too many times. They came up with a lot more creative applications than we could have envisioned. So we wanted to make these resources better. But we were hitting a bit of a limit with crowdsourcing, though, because money is one part of the problem, but another is people tend to repeat, especially if you ask crowd workers to do this job, there's noise, and then there's also the lack of creativity issue. So we wanted to build a better sort of like common sense database, but the question is how? And we wanted to see whether we can squeeze something good out of GPT-3. So what we do is a symbolic knowledge distillation that starts with GPT-3, and then we push it down to this funnel, which somehow generate a smaller model that is better. And in general, that shouldn't be possible. Normally, when you compress down a larger neural network, you get worse model. So how is that even possible? So the reason why this does work is because this funnel is a particular one that has some convoluted process inside, such that it has this critic model that filters out the GPT-3 output when it seems noisy. I'll explain this in a little bit more. But first of all, I want to mention that this notion of knowledge distillation in the machine learning field is due to Hinton et al. 2015, where the idea is when you have teacher neural language model, you train the student model by optimizing this quantity. It's called cross entropy. Basically, what we try to do is you make the student model to mimic the distribution of the teacher model. Simple idea. Except this was originally suggested for classification problems as opposed to generation problem. And so when you have to generate common sense inference in natural language, the scope of the output variable is too large. So then what we do is what everyone else does, which is we sample a few samples and then call it a day that it's a good approximation of the original probability distribution. The nice thing about that samples is that you can connect them up as a graph if you so desire. You don't have to, but we found that human scientists do like the notion of a graph-based, knowledge-based representation, at least in the NLP field. So we do that so that it looks nice to human eyes. And for machine, it's just like lots of strings to train on. So now, how does this compare in terms of quality and quantity to human-written resources? So Atomic 2020 is entirely human-written. What you see on the y-axis is quantity. So first of all, if you just let GPT-3 to spit out database, you can do that super fast, very cheap. But the problem is quality is not as good. So here, the black portion is noise. Green portion is good, but you see that almost, oops, sorry, I haven't done that yet. Yeah, so the black portion is noise, green portion is good. It's about 73% good, if you happen to remember the number. So what we do is we train a small neural network that can throw things out when things look suspicious. So this critic is not very good because it threw out a lot of good portion too, but we can use it aggressively to throw out black portion as much as possible, and the resulting database is still far larger than how much humans were able to sit down and annotate. So at this point, the GPT-3 combined with the critic can do much better than what we were able to achieve by crowdsourcing. And then there's a question of how does that lead to a better student model? So the teacher was loose teacher. GPT-3 was 73% good. It turns out if you train on that loose teacher's output, somehow student already becomes better. That's a bit surprising empirical finding we had. But it was never as good as training your neural network on top of human written resources. So that was the problem in general in NLP field for a long time. Resources were almost always human written because this was the problem. But we found that when we have another AI basically monitoring GPT-3's output and filter that out, then we are able to train the downstream model that is even better than the model trained on human-written resources. So that was quite surprising and exciting finding. To summarize, yeah, in terms of accuracy or scale or the value or pricing, and then diversity of the data, we found that Atomic 10x written by GPT-3 with the help of a critic is just for the first time better than a human written resource in all criteria. And that resource, again, enables a better student model compared to a larger counterpart. So that's the symbolic knowledge distillation. So at this point, we saw one each. And let's now revisit the inference time algorithm, and I'll do the neural logic decoding. So this neural logic decoding, A*-esque, won a paper award at NACL, which actually builds on our previous work called just neural logic decoding. So in this talk, I'll just give you a sense of what it is, but this basically is your, the first author was undergrad student, by the way, at the time. This is basically a search algorithm that even undergrad students can implement. So the idea here is that people, at least in the NLP field or NLP/machine learning field overall, that there's a lot of emphasis on the bigger the better. But when and the bigger the better in the sense that across the board, basically performance goes up. The truth is, there's something about inference time algorithm that we can do better as well. If you use language models, say GPT-3, to generate some sentence that includes a number of concepts, here the example says, generate a sentence that contains all of the keywords, Jupiter, Mercury, Venus, and Mars. And it does understand to some degree, and then it doesn't fully satisfy the constraints. So, by the way, if I ask you to do that, you can do this right away. You don't need pre-training or like fine-tuning yourself. You can just do it right away, right? Even if you never saw this kind of a task before. So that's interesting. And in fact, search algorithms in classical AI was quite important, but it's actually important even for the new systems such as AlphaGo, where Monte Carlo tree search, without which neural network alone would have not gone as far. It's really the search algorithm that unlocks and enhances the capabilities of neural network. So with that in mind, what we try to reconsider is, are we doing good enough job with the search algorithms when using neural language models? And usually people don't really worry too much about the search algorithm or decoding algorithm when using neural language models. They do either just greedy decoding or beam search, something very simple, or sampling, but that decoding algorithm is usually not as highlighted. But the idea is that it might be that we can do so much better by designing smarter algorithms without necessarily having to scale things up so heavily. So especially, we wanted to see whether we can apply logical constraints on the lexical items on the fly to the point of being able to satisfy the full conjunctive normal forms on the fly. And again, humans can do this. You and I can do this. It may take pencil and paper, but we can do this without having to, go train ourselves on this. So we wanted to see, and a lot of actual NLP language generation problems, even including table-to-text generation, are of this nature. So in a nutshell, let's not do the algorithm right now because I don't know how much coffee you had, but I'll just tell you that it's just some search data structure that you have to be careful in implementing this correctly. But it's just a search algorithm that looks at logic constraints. And the reason why it's slightly challenging to implement is because you have to trace whether some of the clauses are satisfied in a way that is irreversible or reversible. So there can be reversible or irreversible satisfaction or unsatisfaction that you have to trace. But anyway, so this is inference time algorithm, which means you can plug and play to any neural network that you just downloaded. The algorithm is orthogonal to a neural network of your choice. It just works right away. So on the common gen benchmark, which is the example we just saw, which is like, given some words, can you compose a sentence that makes sense, which happens to include all of the constraints. So that's the benchmark. And here, what you see is, in terms of the satisfaction coverage, the higher is better. Of course, 100% is what you desire to have. And then on the x-axis, you see the model size. So the bigger the performance goes up when you look at the blue bar. The blue bar is traditional supervised training, where the performance keeps going up as you have a bigger size. Whereas neurologic decoding, so that's green and yellow, either on top of a supervised model or on top of a zero-shot or off-the-shelf model, regardless, the coverage is very high across the board. And then the Rouge and Meteor are some n-gram-based or phrase-based performance measure where higher is better. And for that, again, you see similar trend. What was quite striking for us was that unsupervised neurologic outperforms the supervised method. That's usually not the case in the machine learning literature. But in addition to that, unsupervised neurologic on smaller neural network could outperform supervised approaches on larger networks. So again, I kind of feel like people just assumed that the magic, so much magic comes from the size of neural network to the point that people didn't try hard enough on the inference time algorithms, but it can really unlock hidden capabilities. So that was neurologic decoding, and I'm not going to really do the neurologic A*-esque, but it's basically the A* version of it. If you might remember, or a long time ago, the AI class used to teach A* algorithms, so it's basically that. So we're back to this chart, and the reason why I wanted to do neurologic decoding is because finally I wanted to show you an example of symbolic knowledge distillation that breaks the dependence on GPT-3. Because so far, the symbolic knowledge distillation worked only if there's a teacher model that's so much larger. Then you could train a student model that was smaller, but better. But what if we don't even rely on larger teacher model? Can we actually do better than GPT-3? So, this feels just impossible, but we wanted to see whether impossible might be possible. So here the goal is inductive knowledge distillation. So what I mean by, or generic induction, what I mean by that is generating generic knowledge statement like birds can usually fly. So, this is a form of induction in common sense. So the way we might do out-of-language model goes to something like this. You have to prompt language model, or you have to let it begin a sentence by giving a beginning of a sentence, like a bicycle can, a bicycle has, bicycles, ... So we're going to use GPT-2 for that. And if you use GPT-2 for this purpose, you quickly realize that it's completely useless. It doesn't really give you anything that's good. So what we do is neurologic A*-esque decoding that can give a bit of a lexicosyntactic constraints on the fly to massage the generated sentence to look like generic-like sentences. So no long sentence, no storytelling, no pronouns, no sudden introduction of Sarah, John, going to, I don't know, Taylor Swift event or something. So don't do storytelling, just to say something generic. Though it can be low quality because GPT-2, you might remember, it's really bad. So it said, for example, bicycles are also pedal. I don't know what that means. It's also grammatically incorrect. So again, we need to filter this out because it's low quality. So that's another problem because we can train critic model to filter out. So in this work, we also do this iteration of student being next generation teacher, which generates next generation students, and so forth, because that's how humans also do. So we found that as we iterate this distillation to the next generation, the quality keeps going on. Oh, that would be nice for human students as well. So, this I2D2 produce high quality knowledge. So GPT-2 originally was about 45% good with the help of neurologic decoding, by the way. So even with the neurologic decoding, you don't reach that high accuracy. But after critic, you can be very aggressive and you throw away so much of green portion. You don't have that much left. But we can do this iteratively so that we start having larger and larger data that's of high quality. Okay, so remember our original goal was to beat against GPT-3. That's really tall order. By the way, GPT-3 is more than orders of magnitude larger than GPT-2. So it just looks impossible. Why do you even bother try? Like this seems like something so impossible so that one shouldn't even bother trying. But maybe that's the point. Maybe one should try, just in case. So here what you see is a little bit similar to precision recall curve. And so the red bar is GPT-3, Da Vinci, that is instruction tuned. And so this is a fully loaded version of GPT-3. And it's really impressive. It's almost like staying at the 80% precision zone for a while until it tears off. Whereas our method, I2D2, is able to overpower that. So that's quite a bit of fit, I would say. And we have other works of this nature where we try to go against the GPT-3 by powering up algorithms as well as the data that we feed the neural network on. Okay, so let me now share a bit of comments and strange examples and fun insights. So this pursuit on common sense sort of began, let's just say, 6 years ago when people, at least in my field, thought that research topic of the 70s and 80s shouldn't work on it because it will never work. And in fact, don't even say the word, I was told. And that was because in the AI history, common sense was the beginning research topic that didn't go very well. But it seemed that past failures are inconclusive when they were based on weak computing power, not much data, no crowdsourcing, not as strong computational models, and not even ideal conceptualization or representation schema. So personally believe that this is still moonshot goal, and but it's hard to ignore how well GPT-3.4 does. So brute force, larger network, bigger network might do that. We'll see how that goes, but I believe that you don't reach to the moon by making the tallest building in the world 1 inch taller at a time. So despite the challenges in all the years, somehow we managed to advance enough so that in year 2020, we had the first common sense tutorial given at ACL, which is the premier conference in my field, NLP. And the reviewer number 2 worried that this might be a niche topic and not draw enough of an audience, but it turns out to be the second most popular tutorials of that year. And also, the students who took risk with me turned up pretty successful with their job search. In fact, Verity Schwartz here in Vancouver. Okay, so back to this earlier question that, everything looked almost solved, and it's just a matter of scaling things up. Maybe not. We don't know for sure. One possibility is that maybe we could look at what happened with the physics field. So in 1878, people felt that they almost solved the physics. So much so that when this student, Max Planck, wanted to study or begin PhD, the professor Phillips told him that in this field, almost everything is already solved. So all that remains is to fill a few unimportant holes, he said. The student said, I don't wish to discover new things, only I want to understand the unknown, the known fundamentals. And then he realized that there's a lot to be discovered more and created this whole new field of quantum physics. Maybe, we truly understand a lot about intelligence, or maybe we are just the beginning of it. We don't know. But the dark matter, is among that modern physics concept that turns out to be what matters. And it's really striking how only 5% of the universe is normal matter that we can see and interact with, and the remaining 95% is dark matter that we cannot even measure per se, but we suspect that it's there because it influenced the visible world, even including the trajectory of light. So the dark matter of language, intelligence might be that normal matter is the visible text or images, and the dark matter is the unspoken rules about how the world works. And it is true, by the way, that these larger models do acquire ever more amazing amount of common sense knowledge, so much so that now everybody is writing their papers using ChatGPT. So this professor said theory of mind may have spontaneously emerged in large language models. Immediately, there were other rebuttal papers against it that, wait a minute, if you twist your examples a little bit, then it doesn't work. So that includes our own as well. So what is theory of mind? The theory of mind is the capability to reason about what I think, you think, I think, etc. So it's the capability to reason about each other's mental state without having direct access to it. So here's one really classical example. Alice and Bob saw apples on the table in the kitchen. Alice left the kitchen. Bob moved the apples to the cabinet. So there are two people, two locations. Now, where would Bob think that Alice will look for the apples? Well, Alice left the kitchen, so didn't see Bob moving the apples. So the correct answer should be the tables, but GPT-3, as of last year, would say in the cabinet. So this is the wrong answer. But of course, a lot of these are already fixed. That's just, 2022 is so last year. So the 2023 version of it is that, it's fixed. So here's something about evaluation with the scrutiny, because if you stop here, then it looks like GPT-4 has theory of mind, but I was curious to rotate the last two sentences of the story and see what happens. And GPT-4 says, it's still on the table. So it didn't realize that I reshuffled the last two sentences in the story, and then it kind of figured that, well, people usually ask trick questions such that the correct answer tends to be the first location, not second. So it's overemphasizing on this, sort of like pattern matching. So we have this another paper that drills more into that. And we came up with different variants, maybe 3 people, 3 containers, or 4 containers with 2 people and different configurations. And the paper was written without ChatGPT or GPT-4 at that time. But then we now have a GPT-4, so we measured the performance on it. And so it so happens that it's doing very well on the last bucket, but not as well to the other variant. So it's important not to make a conclusion out of one example or a few examples, but do more systematic evaluation. On that note, I also did a TED talk in which I did this example. I left 5 clothes to dry out in the sun. It took them 5 hours to dry completely. How long would it take to dry 30 clothes? So back then it said 30 hours. So I thought it's so cute. But then everybody complains that no, it's already fixed. So okay, then I'll try a different example. How about if it takes 10 hours to dry 5 clothes, how long would it take 20 clothes to dry in the sun? It's like it's the same question phrased differently. You would think that this should lead to the correct answer, but it's actually incorrect. But that's as of June 18, when I was giving a keynote at CVPR. So I kind of feel like if the example becomes too public, then it does tend to get fixed. Although a friend inside OpenAI says that they try not to do this, or officially they don't do this. So maybe it was fixed randomly. But in any case, but that's as of August 13. Yeah, so August 13, I noticed that version was fixed. So then I thought, I'm going to ask one more, just in case. Suppose it takes 3 hours to dry a shirt and 5 hours to dry a pair of pants. Now, how long does it take to dry 2 shirts? So there's a pair of pants that I inserted. Then, again, it falls back to this original error mode again. I don't know what's going on. But then I saw this Jeremy Howard's tweet message that says, you just really need to give the correct custom instruction that says, you are an auto-regressive language model that has been fine-tuned with instruction tuning, yada, yada. You carefully provide accurate, factual, thoughtful, nuanced answers, and are brilliant at reasoning. So apparently, like humans, you have to really motivate the language model. So I tried that as of August 13, and that was still wrong. But I checked this one last night, and then it's correct as of last night. So maybe motivation works better these days. I thought I will include this in case you see Jeremy's prompt and tell me that, well, it's already fixed. So then I thought, I'm going to ask one more version. Suppose it takes 3 hours to dry 3 shirts and 5 hours to dry 5 pants. How long does it take to dry 1 shirt? So I flipped the number a little bit. And then it goes into this wrong mode again. So long story short, don't tell me that any particular version is fixed unless you try different variations, because these things are not overly stable right now. So the common sense paradox is this, that the following statements might be all true. Common sense is trivial for humans in the sense that all of these examples were trivial for you, but can be harder for machines. But even among humans, common sense is not so common, or at least that's what Voltaire said, and maybe that's why we drew very different conclusions out of GPT-4 capabilities. LLMs do acquire vast amount of common sense knowledge, however. That's actually really important to acknowledge how much more it has acquired than anything available in the wild. Yet, Yang Kun says that it's not as good as a dog, and I think there's some truth to it as well. So the scaling laws are real, denial is futile, but in terms of whether it's going to wipe out VLDB or NLP fields, I think LLMs are amazing. It may be a necessary condition, but not sufficient condition, especially that we may need to design different algorithms around it, because language models are not knowledge models. It's not database models either per se. It's not reasoning models on its own in a very reliable manner either. So we may need to do a lot more work. Thank you.
inspirational talk. Now we have some time for questions, and you will notice that there are two mic stands in the front. So if you have a question, please walk up to the stands, and we'll take questions round robin. All right.
Hi.
We'll start from the right.
Hi, thank you very much for the talk. I was wondering all along, how can we help? How can the database community help be of service to this immense effort you're making to marry AI with language models and make some sense out of it? Maybe comment.
Yeah, that's a great question. I was hoping that eventually I could draw some inspirations from database communities, SQL and all these like structured representations, and then move them to the language domain. And I think there has been some such work actually for certain aspects of NLP problems that are conducive to having canonical data structure. By choosing to work on common sense, though, I found it a bit tricky to come up with good representation that can be represented in a more structured format, but it might just be a matter of investing more into the formalism itself. So there might still be hope that we haven't tried it yet. That would be wonderful to see. Yeah.
Thank you.
Does it? Yeah, thank you for a great talk. My question is about the results you showed on atomic. GPT-3 was much better than GPT-2. How much of that could be that GPT-3 may have been exposed to atomic, right? At the very least, it has probably read the atomic paper and a lot of other papers that have used atomic. Is there a way to know that, and how can we know how much of it is the scale helping and how much of it is basically this leak?
Yeah, that's an excellent point. I guess we never know since OpenAI decided not to open their training data. One can guess or suspect that there's some such thing going on. In the sense that for the theory of mind case, I see the slide is not up anymore. So the theory of mind case, I think some people found, the psychologist thought, wow, ChatGPT is so great. And this might be a case of seeing a lot of canonical examples so that it can do well on this, whereas the questions asked by this professor at Harvard, Tomor Ullman, were not as canonical. So we can guess based on that. We can speculate. We're never sure, but yeah, excellent point.
Thanks for the nice talk. I have a question regarding the first part of the talk on arguing with the language model to make sure that you can get out something correct. That graph of thought, so to speak. I was wondering how robust this method was to how you pose the question, right? Because all these, and more general question is chain of thought, tree of thought, and graph. So how robust they are, in a sense you pose the initial question particularly. And my second question is, what's the limit in this approach of sort of prompting to get correct information? Is there any limit where you think we can get the correct information through this way?
I'm not sure if I could parse everything, but the question is how robust are these sort of like graph-based chain of thought reasoning or generally improving the LLM performance. So it's better than not doing it, but it's not like perfect at all, in the sense that the performance is still far from 100% or human performance, which is far significantly higher. So we are still not sure how exactly we can close this gap. some people just wait for GPT-5, that once you have a larger model that has seen all of these benchmarks and beyond, will definitely generalize better. But it might be that there are, so I'm hoping that we somehow as a community find a smaller version that acquire knowledge in a much more compute efficient way, and then do a little bit more, I don't know, like a principled operation on top, so that it can lead to similar or better performance.
For the great talk, this is Estevam. Question regarding the point you raised here, and I agree with you. Nowadays, we see lots of people cherry-picking things, and now, even when we are reviewing or attending to papers, you see more and more papers like, oh, I found out that GPT-4 doesn't do that, or, dude, it does that, and things like that. So, to me, I would like some thought here on first. How long do you think it would go? And second, more importantly, maybe, how can we as research community try to reinforce to the research community that just getting a black box is not even open, as you said, and now driving all our efforts towards that might not be the best way to go. So,
Yeah, indeed, I agree that some people, I mean, even for the error cases, sometimes the people, when I show the theory of mind example, for example, some people's reaction is that, well, GPT-4 actually knows the correct answer, but I should have asked more politely or provide more hints, then it knows the answer. Yeah, it does. So I would just, my reaction to that is that GPT-4 does have a capability to latch on the hint if you provide more explicit hint around it. So that is good capabilities of reading comprehension on GPT-4's side. On the other hand, it's a bit hard to conclude that robust theory of mind is there based on those cases, because a lot of the times the theory of mind is really about reasoning about things when the hint is not so overt. And so it seems that the community does need to have a little bit better understanding about the fact that although GPT-4 is so amazing in so many ways, it does have some flaws. And the mistakes can happen in the most surprising way. And perhaps that's one of the biggest challenges that both the VLDB and NLP community do encounter, which is that we don't know when it's going to make a mistake and why right now.
Yeah, it's closed, yeah? So shouldn't we put attention in something we can explain? Because we will always find another example in something that we don't understand.
Yeah,
Anyway,
I agree.
Thank you very much.
So, I'm so sorry because we're running a little bit out of time. I know you have a lot of questions still for Yejin, but lucky for you, Yejin will also be in a panel this afternoon, this panel on LLMs. So I hope to see you there so you get more chance to interact with Yejin. So, but for now, let's give it up again for our keynote speaker.